Hello, friend. We will continue the unfinished topic again. Let's write here our other topic. It will be quantization. We will read something about it too. Quantization. Okay, which is helping us to put our values, our uh, our sampling points into the one value, and we can increase or we can decrease in one value. You can think like just think we have 25 point and there is lots of number, and we have some float numbers, so we can say 2.5372, we have minus 5.7523, something like that. And so you can round off them. Anyway, we have lots of number. Just think, if you want to represent them with the binary numbers, how we can do that? We have some way to represent it. So we can do quantization and we can put them in the some kind of number. You can think, if we have x-axis, it's all about volts, and y-axis for the time. We can think for x-axis, normally we have 100 between minus 100 some values, right? Okay, now just think, we don't want to put there 30. So normally we told there we have 330 seconds, milliseconds, and each 30 seconds, milliseconds, we have one value, right? So one sample. Now I will tell you, we will represent now these all numbers in time, like 330 seconds. Each 30 seconds will be one binary number. We can think like what, I will explain you. Just think we have, so we just want to put them, we want to round off them in the one number, like think we have 27 and we have 23 and we have minus 24, all will be just 25. We will represent with 25, and 25 will be one binary number. It, again, I'm saying you, between minus 100 and 100, uh, between these values we have also zero there, the point. So there is will be 9 point, right? We can think like we have 0 to 0 to 9, we have binary numbers. We can think like that, and let's do it. I will really show you all of them. Let's write little bit, but before write, just tag it in the blue. This is our subject. We'll speak. This is important, really. You have to learn it. This is really important. Let's say after sampling, yes, we are still left with we are still left with a wide range in the with a wide range in the amplitude domain. The y values, let's put it there. The of next step of yes, quantization reduce quantization reduce let's say reduce that continues that continues continues yep, amplitude domain amplitude domain. Let's write it like main. Where is it? Right here. Yes, domain into discrete 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 levels. Amazing. Now all we will solve together. Okay, don't worry. Really, you will understand all kind of subject about it. You will understand all the values there. Really, conveniently and efficiently, you will get all kind of benefits from this topic to improve your skill for the future. For our simple signal, where amplitude varies, right, from minus 102 to 100 volts. I told you. Yes, the not volts like that, it's volts. Yeah, now say we can apply, let's come down, apply quantization interval, this is good, of 25 volts. Yes, this is the important point. We will tag 25 here, all the time it will go 25, 50, 75, 100, 25, 0, and all the way it will go like that. If you have minus 23, it will be 25, okay? But it's for binary, okay? Now we will go together. Just don't worry about it. You will see all of them, okay? Okay, let's come here and let's take this example from here. Let's bring it down. Come on, right here. Yes, and then just we need to tag, what is it? 1 minute, right? This one. This will look very bad. Sorry for that. Now, let's say this one is pink. Maybe not pink. You can think it's like, you can say purple. Say purple. Okay. This one. This one will be our quantization mode. So just think, if it is the first one is just this one, it is normally what? It is normally 7, right? 0 millisecond. Uh, we just equals to 7 volt, and now it will be 0. Okay, because quantization, it's just tagging some values in one point, because we want to tag uh, some analog information to make them digital. Okay, because just think, now I am speaking and my sounds waves is going there, and some details have in my sounds. So my voice, there's, if I do something like that, and all the details is going there, it's going there, but computer cannot represent all details, because we have quantization. Quantization just saying, if there is signal like 23, or you can think like hertz, or you can think like some volt signal, I mean frequency, it's taking this frequency. If it is 23, it will think this is 25. So computer don't tagging it like 23. Now some modern computer, okay, we can think too much, we can discuss this subjects, okay, it's really not problem, but I'm just speaking directly for about now and for about this basic subject. So computer can tag it with 25. If we have 45, it will tag like 50. Also, we can represent or we can indicate. Also, we can define. We can indicate also in interval of quantization. So we can say uh, like 10x, 10, 20, 30, 45, 50, something like that, or 15, 30, 45, 60 can go also like that, also maybe 5, 10. But if you put there lots of quantization uh, numbers, then what will be there, uh, we can leave some problem also with this way. I will give you very good example to understand really it. So what is, just think if we have lots of point there to do it, then we will use lots of binary number to represent the situation, right? So if we have lots of things there, then we need to put there lots of binary numbers to represent each number in quantization. Anyway, all we will do together. Okay, now just think this is 7. No, this is 7. This point is 7. If you do quantization, it will be 0. So because we will decrease, so we will decrease or we will reduce it to 0. And also this one is, the second one is uh, the 95, but it will be not just think this point is 95, but we can't represent in binary like that. We can do it, but we have some point like 95 point like that. I will show you like 95 point and some number. So in binary, really, it will be very difficult to represent. But in binary only, we can say 100 for that, right? The 100 will be this point, and just think this one is now where is it? Where is it? This now here, and this point is just 7 point some number. And really, this is difficult. Computer cannot store lots of things like that. It will be lots of value there. It's really dangerous. Anyway, so let's think. For that, we are saying sometimes our sounds waves frequency is not going sometimes good. Some sound recorder, voice recorder, just think like that. Maybe I can show you some example. Just say recorder. Okay. Hey, hello, how are you? I'm just okay. What do you say? Hey, lots of. Hey, just check it. What will be? Hey, hello, how are you? I'm just okay. What do you say? Hey, lots of. Hey, hey, hello, how Look are at you? That. I'm just okay. What do you say? Hey, lots of. Hey. Have you seen waves? This is just going all the way like 10, 20, 30, 40, 50. There is so we don't have 10, 11.65, 12.1992, also maybe 14.20, 15, and some point numbers. I mean, rounding numbers. Now, I think you get what I said. This so in quantization, we are thinking this one is not 95. This one is just, let's delete this one too. This is will be here. It will be this place. So it will be 100. It will not be 95.986 and some kind of these things, because computer cannot represent in binary numbers. We don't have too much data to store them in this place. So just in file, we can't really put there lots of them. Maybe in the future we will we will so we can improve our skills to the improve to the new technology to make to take this sounds very good than before in range of in extent range of extent area. Let's we can do later. Okay, anyway, so it's all about data. Okay. Okay, the other one will be not will be minus 106. No, not will be minus 71. It will be um, 75, minus 75, and minus 75 will be just think like here. Okay, in this place. Another one not will be minus 100, 6. It will be minus 100. So it will be maybe here. We can think like that. Okay, just I'm representing it. I'm just trying it. Okay, and then just think the other one will not be 97 minus 97. It will be 100. Again, just think it will be in this point. So all the way it's going like that. The other one is 70. It will be 75. Maybe you can think like this one is here. Another one will be not 29. It will be 25. Just think like that. Another one. So all the way, I think you understand what I'm doing here. Other one, not will be 6. It will be just 0. Which one is that? I will look at now there. Yeah, I think this one. Let's look at the other one. It's here. Yeah, the first one will be here. So let's look at that. This one. Normally we represent with the decimal number is 210. Let's say for it, it will be, so it this is representing with the volts is like 6, but 6 will be 0. Okay, because I told you 0, 25, 50, 75. It's all the way going like that because we are doing quantization. We are just rounding them in the one number to represent with the binary numbers. Anyway, the other one, just 24, it will be 25. Just 25 can be here. Sorry, this one. Okay, and the other one, where is the other one? Yeah, other one is 74. Minus 74, it will be 75. It's again same, not too much away from this, not too much far. Minus 31, it will be 25, maybe at this point. Yes, minus 25. And other one will be 25. It will be here. Okay, you can think like that. Oh no. This one is safe. Let's do it. Let's take it. Oh, it's crazy. It's already there. Okay, this is the way, okay, to understand this concept. Now I will show you with the details what we done here. Let's take again pencil. So the same point again for things. Now let's say Let's come down. Okay. Where is our words, please? Oh, it's there. Okay. Yes. Let's say now the 12 points all have y values that are multiples of 20 multiples of 25. This is the important point. I told you it will go all the way like that. Now, what we have to do, let's go up and take this information because it will help us now understand think. Let's take it. Let's go down. I'll go right here. Yes, this here. Now, the first one not will be 7. It will be 0 or 25 or 50 or 75. So 75 or 100. It can be only that. Let's say 7 can be 0 because it's closer. 0, not 25 and not other ones. 95, it's I told you there is lots of number, so it is floating number, and we just have to put there 100. I told you because all the y values that multiples of 25. This one is will be minus 75. Okay, not positive 75, is minus 75. The other one just will be minus 100. This one will be minus 100 again. Yes. This one not will be 70, it will be 75. This one is just 25 minus 25. This one is not 6. 6 not closer 25. It will be just 0. And then it will be 25. It is very close to the 25. And this one is will be 75. And this one really close to this to 25. And this one will be 25. Okay, now what we did here, this is now in quantization. Let's write something here now. I told you now our things change. I told you also here. Now let's write something here together. Okay. Let's take the pen. Yes. Let's say the ideal quantization. The ideal quantization interval depends on our use case and physical constraints. It will not be good. Yeah, let's come down. Constraints if there is enough space to represent thousands of different y values. And we can use then we can use a very small quantization interval. What we said here. Saying the ideal quantization interval depends on our case and physical constraints. If there is enough space to represent thousands of different y values is too much, well, then we can use a very small quantization interval. Like what? Like that. Just think we have thousand values. We can use small numbers. Like what? Interval numbers, I mean. Like five, like two, like three. Because just think, we have lots of number. Like just think we have 25, 27, 28, and 124, and we have just think we have how many we can say 352 and 565 and 720 point and something number. So we can't do it 25 multiple of 25 because we will lose lots of detail about our data. We don't want it because just think you will speak lots of things in your waves, in your sounds waves. It will take just some numbers, some range of numbers, interval of some number, interval of some way. So just think I will say, hey, how are you? It will take just hey and are you. It will not take how maybe there. Okay? You can think like that. I hope you get it. Because I can really I can say you something like that. I can give you some sample in this way. By the way, this is a little bit complex and just try to understand, okay? If there is limited space, then we can use a large interval. What we are saying here, if we have thousand values by values, just saying thousand sampling place point, and if we don't have, so if we have limited, I mean limited space, just think we have little place to represent it, then what we can do, really we can't do anything, just we can do 25 to 20, 15. Just think we have thousand values there, thousand point, thousand sampling. We can represent them. If we have limited data, we can represent them into the 15, into the 10. Yes, we will lose lots of data there, but we can't do anything. So we can discuss it, okay? But this is the reality. If we have lots of area, lots of data place, I mean, if we have space, then really we can use very small uh, numbers for represented. But if we have uh, limited space, then really we have to use large interval. So because yeah, we can do it. If we have 32-bit place, just think like that. If we have 32 bits, with 32 bits we can represent lots of things than 8 bits. In 8 bits we have some limited, right? In 8 bit, just think you have some small waves in your sound, some small details. With 8 bit you can represent till some quality, but in 32 bit we can represent lots of uh, things. We can represent them, by the way, okay, step by step. And can be lots of details in record sounds and some program or some computer program. And 64-bit will take lots of details, and it will go all the way like that, okay? Yes, it is like that. And say interval The quantizing, the quantizing step always introduce introduce some amount of quantization error, which is measured, which is measured. Let's take it a little down. Maybe it can be some details then you can see better. Which is measured by comparing the actual signal, by comparing the actual signal, which is measured by comparing the actual signal value with the quantized mm, value at each samplet, value at each samplet point. Point, right. It can compare it really. However, 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 some level of quantization is some level of quantization is yes always necessary for storing, always necessary necessary for storing analog data in digital form due to the finite nature of the computer's memory and its numeric precision. Precision. Let's say Apple. This is the important point. Okay, our other topic. So here we can speak also about it. The quantizing step always introduces some amount of quantization error because which is measured by comparing the actual signal value with the quantized value at each sample point. However, some level of quantization is always necessary for storing analog data in digital form due to the finite nature of computer's memory and its numeric precision. It's good. Let's come down. Say binary encoding. Yes. Now what we will do here, now we will go third step, how we can represent with the binary encoding that all steps, that all quantized number before decimal, then we did it quantized number again, and now we will take them into binary number. When I speak, my sound waves will go there with some decimal point, just you can think like that. Okay, you can do some brainstorm. Anyway, then it will take sound like 27 point some number. It will represent 25. If I have 65 some sample like in my sounds, it will take 65.7 blah blah something like that. It will tag it like 75. It will not see it like 65. I told you if you have lots of space, just think you can like I gave you the one example about 32-bit. If you have 64-bit, then we can really do 2, 4, 6, 8 all the way like that. We can quantization. We can quantize it to represent number. Then we can tag lots of details in the sounds. Okay. I mean the quality. If we have lots of space, and if we are using their so closer interval, sampled interval, like each step it will be like 2 by 2. It's multiple of 2. Then it will give you good quality. I mean, like what, it will give you lots of details, but maybe quality can change. Okay, we can think about that. So the quality uh, can change. Okay, quality situation can change because it will be little fast than big space. Okay, let's say binary encoding, and let's do it blue. Other topic. Now we will go through our other samples, how to solve this problem. Now here it will help us. Now, okay, now let's start to write it. Yeah, we can write here, I think. Now that bring brings us to the final step. Binary. Well, what happened there? Yes, just take it back. Yes, binary encoding. If there is a limited set of, if there is limited set of quantized by values, the computer does not not need to store the need to store the actual 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 value. What it's saying here, it's saying if there is a limited set of quantized values, the computer does not need to store the actual value. I think you got it. If there is a limited set of quantized, limited, okay, then computer does not need to store. You don't need so. Instead, it can store. Instead, can store much smaller value that represents quantized 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 by value. For this signal, for this signal, quantization interval of 25 resulted in 9 possible. I told you we have minus 100, minus 75, minus 50, minus 50, minus 25, 0, 25, 50, 75, 100. We have nine possible y values. Yes, we can map the 9 values. We can map the 9 values to the binary numbers 0, 0, 0, 0, 2, 1, 0, 0, 1, like 1 times 1, 1, 2 times 0, 4 times 0, 8 times 1, 8 times 1 plus 1 times 1, it will be 9. And also you can think like what, power of, yeah, really you can do it. Like think we have 4 bits, right? Here. Power of 4, no, n power of 4 minus 1, it will give you again same solution. So it will be 4 power of 2 minus 1, it will give you 9. Okay, let's go down. Now I will show you with the example. Let's take let's take maybe the first one is not good. Maybe again this one, really we don't have chance to get others. Okay, this one is okay. Let's duplicate it, come down. Okay, what we will do, here. Now we will delete this 100 and all values here. We will do together all of them, okay? Now, the important thing here, just delete the 2. And also from there, delete this number, 100. Let's come down. And where is our place here? Okay, we come right here. Now we have this value here. And what I want to do, just tag it here because it will represent this place, okay? And now I will draw this place too. And don't worry, okay, I will prepare now all of things here. It will be 0, 1, 1, 1. Other one will be 0, 1, 1, 0. Other one will be 0, 1, 0, 0. 0, 0, 1, 1. 0, 0, 1, 0. 0, 0, 0, 1. 0, 0, 0, 0. Like that. Now what I want to do, let's come here and put there something. But it will take lots of time if we do it. I think maybe we can do from here, like that. Yes, but then it's 1 minute. This one will be there. Maybe let's add it. I think it's not possible, okay? Just think the our values is here, and this one will be here. It will take lots of time, but okay, let's delete it and delete it. Some values like that, and this is here. Okay, this is really not good, but just you can't think it like that, okay? Let's do it. We can take them little like that, but maybe let's first think about the value. This mm, let's think this one is, yeah, this one is can be here. This one is can be bigger than little. This one is also can be in same point like that. Yeah, again same point. And this one can be there, and this one will be again there. This can be here. Okay, my friends, just think some point will equal what we done here. We did it. Okay, the all values will notate that. Okay, that this one will represent 8 bit, and this one will represent 7 bit, which is what we have. We don't have anything there anyway. It will be also small. Normally it will not represent any number of 7 or something like that. It's just there. Okay, anyway, just think we have some point here. Maybe do it with red. Say this one is that. I can do it. Yes, I mean, you can think like that. Okay, we have some point here, and just it's representing with the binary. Why it's okay? I believe you got it right. This will represent with this numbers. I mean, now we are not using this 150, 180, 210. Now we are representing with these values. Okay, this is all. Let's say now we can represent our numbers. Let's take little up. Okay, yes, let's take again little up. Maybe this place, if I'm right. Let's write something and come down. Now we can say encode the signal into this binary sequence. Now let's look at here. The first one, maybe, yes, the first one is 0. The other one will be 100. The other one will be minus 75. Now we know the point here. What is representing 0, what is representing 100, right? We know all the information about here. Just we have to compare our y values with the x values, okay? You can think like that. So what I'm saying here, I will be clear. Wait, maybe I can take this. Let's take it and come down. Really, I want to show it you. let's come down, make it small. No, why it's like that? I don't know what. No, let's let's do it like that. Okay, just think it will be here. 0 representing 0. So this one is just that. Now I will write it here also down. The first one is representing 0, right? 0, where is the 0? 0 is that. 0, 1, 0, 0, okay? It's representing with the 4. 0, 1, 0, 0. The other one will be what? This other one, 100. Where is our 100? Now you have to find position of 100. 100 is here, right? It's coming like that. Normally we know our 100 is there. So it's 30, I mean, because it's going 0, 30, 60, like that. This one is will represent, 100 will represent 1, 0, 0, 0, like 8. And then let's come right. We have 75. So 75, we can represent it with the what? This one here. Have you see? But it's saying minus 75. Let's go to the displays. It will be 0001. This is the that value. You can think like that, okay? So that value normally have to be here, but just I told you, I it will take lots of time. Okay, it will be here, okay? So let's write it. It will be 0001. The other one will be minus 100. It will represent 0000. And again, other one will be minus 100 again. Again, 0000. Other one will be again 75. Will be 0001. Right? Other one will be, what will be other one? 25, 0, 25. So it will be like 25, 0, 25. So I mean, this place, let's see, where is the 25? What do you think about 25? Where is the 25? You can think like that. Okay. So the point here, 25, will be this one here. Okay. Why? Because I will explain it to this point. It is minus 25, right? Yeah, minus 25, 0, minus 50, minus 75. It's all the way going like that. And just think it will be 0, 0, 1, 1, minus 25. And then we have 0, 25, 0, normal 25, 0 will be, which one will be 0? This one is 0 over 0, 0, 1, 0, 0. Okay. The other one will be 25, normal 25. It will represent with the this value 0, 1, 1, 0, 0, 1, 1, 0. And what we have later, 25, minus 75, minus 25. Minus 75 is that. And we have minus 25 again, which is that. Right, let's come down. 25. And then we have 25, which is 0110. Okay, now we can delete it. So, and also, sorry, this one is I think one I wrote wrong here. The last one is 25. 25 is wrong here. Where is it? This one, I think. It's now. This one is 6. One is 5, only 5. Oh, this one is really wrong here. Maybe this point we can really look at. The first one is 0. The other one will be 100. This is okay. The other one will be 75. Minus 75 here. Again will be 100. 100. Minus 100. So 2 minus 100. Then we have 75, which is this one. Okay. Yes. And then we have 20 minus 25. That is right. And then we have 0 minus 25. And then we have 0, which is this one. Okay, then we have 25. Yes, this one will be 0, 1 and 0, 1. And then we have minus 75 and we have minus 25 again, which is there. The other one will be 25, like 0, 1, 0, 1. Okay. Now, have you seen if I have sounds like that, computer will represent all these numbers like that. When computer files, so in binary files, I can show you. Let's see. It's in binary and it's super binary. All we have this files. Okay. Let's say ls bin. It's not such file or directory. Sorry, I have to go inside it. Yes. But what I did, cd bin. Let's go back. Oh, I'm in home. Let's go again. Okay, clear here and say I am I. Okay, yes. Now, what I want to do, we are now in the root of this place. Let's say, let's go into the binary and let's check. Okay, just think we have sounds file here. Okay, you can think like that. Just think, okay? I don't know because where is the now sounds file here. So just think, but in here we have, okay? I don't know where is it, but in this place we have. Just think, which one? Just think it is Znev or Zmor, this one, okay? This is our sound file, voice files, okay? Voice file or sound file. It is binary, okay? Just you have to think like that. If I'm speaking and if the computer want to tag this analog data to into digital data, it's just writing some binary code. And just think like I'm just saying cat more. Okay, but I think this one is looking like normal programming. Let's come again here. Maybe go inside cd mcd no cat mcop, not such file, mcat, sorry. Yes, cat mcat. Okay, this is binary here. Look at that. Now we have lots of things here. It's all binary, okay? Binary, it's representing binary numbers here. So this is the important point. Computer can read all these values, all this thing, okay? You don't know what is turning here, right? You don't know really what's happening here. Do you have some idea? Of course no. Now computer can understand these things. What is it really? There is nothing you can understand, but computer really can understand this N, H, O, P, P, X, Q, some language there. Computer know what is turning there. Okay, that's what just say. Okay, let's try to find maybe sound file. No, really, there is not sound file. Okay, I think let's go into media. I think it's same again, and some number there. Ever file, drum stack, log, swap files, essays, what major, Hebrew files is. Let's say which one is Python 3 and program files, program data, OneDrive. Let's go back and let's go back again. Let's go back and yes, again come here. Let's go to the root, but for go to the root, sudo root, yes, root directory, yes, proper sudo root command not found. Let's say sudo root. Root is a directory. Okay, think I think we can find it later. Okay, really, just maybe we can go user because we have also there some binary files. Okay, we have here games file, library, and local share and some kind of other thing. Let's go to the in library, this one, which is this one. Maybe in games. Okay, let's go in the games. I just want to give you some examples. Sorry, I was been here. Genome Sudoku. Let's say genome Sudoku. Yeah. Control center, image mounter, log, scaling, all of this just files, and really we can configure them and we can do lots of things with them. And just let's go to the genome. Let's write it genome ion. Yes, look at that. All these files is just the game. Okay, one game. Computer really know what is turning in Sudoku, in game and in kind of things. Okay, let's go back. Maybe let's go a little down. Let's say home cd other fair. Okay, the point is that we will write a little bit more. Let's come here. Just I give you some example, okay? Just try to understand it like that. this point, let's say for a computer to understand that sequence, our our digitized version would would also need to include description of how to sequence was and sampled and encoded. For a computer to understand that sequence, our digitized version would also need to include description of how the sequence was sampled and encoded. Yes, we can do it with what, with the frequency curve, some curve. It's just so computer can compare actual data, actual diagram, and new diagram. I mean, so quantized data to actual data. The computer can just compare them. What is the curve of differentiation between them? Okay, let's say you get it, and let's come down and say this encoding this encoding uses 4 bits per sample per sample. So I told bits, but sorry for that. It's patterns. Okay, you can think like patterns. I told for 4 bits, it's representing 8 patterns there, 8 possibility, 8 number. Okay, per sample. The number of bits per the number of bits per sample is also known as bit depth. So, what it's saying here, the important point, this encoding uses 4 bits per sample. The number of bits per sample is also known as the bit depth. Okay? The lowest bit depth the lowest bit depth is 1, which depths just tag depths here, no, right here, which, yes, which can only describe 2 values, right? This is pattern 0 or 1. Okay, the bit depth standard bit depth for for telephone calls is 8 bits, 8 bits, which is it can how many pattern can be in 8 bits? Just think about that. How many values can be in 8 bits? 8 bits, just think about that. It can store there 256 values, right? I mean that. And let's say 8 bits values. Was it? And the recommended bit depth for YouTube music videos is 24 bits. Wow. And really you can think like 24 power of 2, that will be lots of value. So it's just like over 16 million values. It will take lots of detail. 60 million values, just in you speaking, stacking lots of values there, lots of from your sounds. But if our interval of the quantized data just if it is multiple of 5, multiple of 7, it will take some detail. Just think if we have 0.0001 multiple of 0.00 some numbers, it will take lots of details from your sounds. It's YouTube music like that, you can think. Okay, now we can also represent it, believe me, with 3 bits also. I told you the first one because I can show it you now here. Normally what we have here, we have some empty place for represent. Just think the 75 working for some value, right? The 100 working for some value. But if you check, we don't have any value to represent about 50. 50 is just enough for this data because we don't have any value with the equals this 50 or minus 50, right? Just delete minus 50 and normal 50. What we have then? We have 9 minus 2, it will be 7. Now we have 7 point and we can represent 7 with 4, 2 and 1. It will be 3 bit. So we can reduce our bit. Then you can think like our store. So it can take little store. So we can store it with the little bits, okay? Not 4 bits, it's more than 3 bits. Yes, our other topic is reconstruction. Let's come a little down. Okay, let's say reconstruction. This is the important place. Now we will reconstruct it. We will, I mean, we will configure it again. Okay, we will reconstruct it. So that, let's do it blue. Let's come down. Let's take this. Let's put down and start to write again things and things. Okay. Let's come a little here. Okay. That's right. We often we often store analog signals in digital storage, digital storage, so that we can so that we can reproduce choose yes them later, like play later, like playing back and back on audio file or this audio not audio audio file, or displaying an image. Yes, it can be really like that. Displaying an image. Um, when a device want to convert, when a device want to convert, wants to convert. Okay, digitize the signal back. Digitize it. Signal back into an analog signal. Into an analog signal. It will attempt to. It will attempt to. Will attempt to reconstruct the original. Reconstruct to original. Construct to original continuous signal. Continuous signal. So let's say here we often store analog signals in digital stores so that we can reproduce them later. Of course, like playing back on audio file or displaying an image, it's something like that. When a device wants to convert a digitized signal back into an analog signal, just think we have some file there. We already save it into file. We got all this analog data into digitized data. We just represented them with the binary numbers, all now in the one file. You can think like this sounds file or something like that. The when, this is the important place, when a device wants to convert a digitized signal back so into an analog signal, it will output, I mean, maybe it will input or it will output. Again, you just think you spoke something, it's just recording your sounds there, and now you want to play it again. Now when you want to play it, it will just convert again this digitized signal back into analog signal, so it will reconstruct again this original data to original continuous signal. I mean, it will just reconstruct it again. Okay, anyway, I mean, it will be quantized data. The reconstruct data will be our new data. So let's say for this signal sample simple reconstruction strategy construction strategy strategy could interpolate, could interpolate smooth, smooth curve. This is good information. Truth to quantized points. Quantized points. Yes. Signal a simple reconstruction strategy could interpolate smooth curve, so it will just work on with this smooth curve. It will just go on the uh, how I can say it, this curve, smooth curve. It will go all the way on the quantized points. It will just follow it, by the way, and you can see the original data between what is different between original data, how much far between themselves. Then we can understand our quality will be like what, our details, how many details we will take in sounds. It will be like that. Let's plot it in some way. Can do it. Okay. Let's come here and tag it. Let's bring it down. Yes, here. Okay. Let's delete this information. Maybe this here also. Yes. Delete it too. Small things there. Let's delete them all the way. Yes. And this one's here. Delete it. And really just delete them too. Let's tag it them. Maybe this one's also. Let's tag it also that. Okay. We can tag also this one there. Oh, it will delete all. I'm just worried about that anyway. Anyway, it's so this one is also I will delete now. Okay, this is our point. Now, what I want to do here, I will show you our new data, how we are doing with the smooth curve, uh, truth to quantized points, how we could interpolate it. Okay, it will be like what, like that. Just think, mm, which color? Okay, it can be blue. Let's say this one is blue. Okay, this is our reconstructed uh, data. It's coming all the way like that. And but anyway, sorry. First, I have to do point here. This will be point. Just think like how I can do it. Okay, this point, also this point here. We have also here 1 point, and also 1 point here, 1 point here, 1 point there, 1 point here, I think, not too much here. Let's go to the there, 1 point we have here. Where is it? Yes, 1 point here, and let's put there 1.2 here, and let's come here 1 point here, again 1 point there, and last point will be here. Okay, let's do it. Which color? It can be green. Our smooth curve will be like that. It's going all the way like that. And just think it will now will follow it to the will come here, and it will again follow this way. It will follow the other one, and it will go to this one, and from this one to this one, and we'll go there again. It will follow this way, all sample it. Now it will come here. So this is mm, our quantized points, and it will come here. It will come to the here, and all the way like that. Have you seen? We can interpolate it with the smooth curve through our quantized points. Now we know our data, right? Okay, let's do some black again. Do this one is here, spring here. This one is here. Okay, I think we have here this one again, this one again here. Okay, is this one. Okay, we can represent it like that. Let's write there something again. Come down. No, I think we got it. Like what is turning here, right? You know now what is turning here. I think I'm sure you get it. So now we can say, how well does that match? Does that match original? Yes. We can we can overlay curves to see the curves to see the difference visually. So converse to see difference visually. Yes. Now this is good place. Let's do it. Now our original one is that. Are you remember? This one. This one, the original. Now we will bring them next to next. What is bit different between them? We will check it. Okay. How we can do it? Okay. I will tag this one. Let's tag this. Bring it down. Okay, here. Let's no. Let's delete them. Delete this one. Delete it. Delete this one too. This one again. Where is it? Yes, here. This one. Again. Delete it. Yes. Okay, let's tag from here. Color purple. Maybe purple. Yeah, purple is good. Okay, now We will plot our original data. Just think our original data will be like what, you know? So here, mm, we can say, look at that. Just think like what, you know? Our original data will go like that. No, this little bit art. I don't know how to solve it. Yes, something like that. And then it will come between them to this place. Really, it will go all the way like that. And it will just go to this place little bit and little bit from this place and something like that. And this is just some example, okay? This is not good, I believe that, but just try to understand the original data. Okay, what I want to tell you here, the purple is indicated here, notated, original data. This one is coming little bit from left. Our quantized data is going from right. I told you we're just representing 27 in quantized data with the 25 because everything multiple of 25, right? But in our original data, all the values is staying all like the same. So it's, you can see our original data is going like that. Our quantized data, our reconstructed data is just green. It's going different than our original data, but not too much different between them. We can say for it, maybe let's come to write it down here together. We can say the reconstructed signal looks very close to the original, but misses a few details. Yes, because why, you know, I told you normally it's just original data is saying 27.25, 32, and some small values after, so floating numbers. Now we just representing them with the 25. If there is 27, if there is 27, if there is 24, if there is 26, all the time we are saying them this is 25 because we are just quantized them in the one value. We just representing like that because we have to say computer this is that number. If we don't have too much space, if we have limited, really we have to put it there like that, because if we can't so I mean we can't represent all pointal number, I mean just rounding numbers, like think we have 3.7, 3.4.3.7456, and kind of this number. How computer can store this number? Please tell me. It is not possible for now, because lots of number will go like that. Maybe some number, just think 1 divided 3, there is will be infinity number. How computer can represent it? This is not possible. For that we are using quantized. This is helping us to represent things there. Yes, we can lose details, but it is possibility. So if we increase our bits in the future than today, then we can represent lots of details, lots of quality, right? Okay. If we can decrease the sampling, if we can decrease the sampling interval and lower interval and lower station station. Yes, it's saying if we can decrease the sampling interval, I mean, like not it will not will be 12, it will be 10, it will be 4, it will be 6, like that. And it's saying if we do it something like that and lower quantization, just think it's not will be 25, it will be 10 or some different number. Quantization, lower quantization error, we can bring to we can bring the constructed curve closer to the original signal. Really, if we try, we can compare them, and really we can find good solution here. Just we have to think little logically, and we have to do some brainstorm to find really good values there to improve our smooth curve, to bring closer the original data. Really, then computer can represent your sounds very good with the details also. So with the reality, I mean, it will not too much loss there. So let's say we could also use different. We could also use different strategies different strategies for reconstructing um, reconstructing what is that? Reconstructing. Anyway, I'm sorry if I so forgive me if I'm writing wrong here. I think the signal. Okay, for constructing the signal. Yes. The last one is crazy. We could also use different strategies for reconstructing the signal. Okay. What is that? Okay. What we did? Summary. We can say here summary. But anyway, I will tell you what happened in summary. Okay? I will tell you now. The first step of sampling converted an infinity stream to infinity sequence in quantization. So what I'm saying here, first step, we did some sampling, converted an infinity stream there to infinity sequence in quantization. Then the values in that sequence were approximated, right? So we did some 25, 75, 50, something like that. Finally, the values were encoded into bits for storage on a computing device. At same later point, a device could interpret those bits to attempt a reconstruction of the original infinity stream of continuous values. Whenever we convert analog data to the in digital data, whether it is audio or visual, our goal is to sample data with enough precision. So precision is too much important than all, because this is the quality also, so that we can reconstruct it later at the desired quality level, but not exceed our data storage capacity, right? Capability is also important. So landline telephones use relatively low sampling rates and bit dips, since the data must travel our telephone lines, whereas movie directors record film at very high sampling rates and bit dips, so that they may reply it in giant screens later. So also you can find a device near you that converts analog data into digital data. You can work with the recorder. What sort of sequence constraints does it have for storing and transferring of the data? What sort of detail it's lost in the digital? So what it's lost there, just check it. Okay. So now I have a question here. We can look the questions. Just I will do two questions, okay, in this point.